Our next speaker is Ted Johnson. Ted will talk about dispersive wave dynamics of coastal flows. Ted, the floor is yours.
Thank you very much. The organizer reminded me that I like it what David said. It's great to see this group back together again. So what I want to talk about, I've talked about some of this before, some of you have heard some of this. It's joint work with Rob McDonald, Ollie Southwick, Sean Jamshidi, and most recently with Michael Nguyen. And I'll talk mainly about the recent work, and I'll talk about the bits that we don't understand very well. So please comment. So the basis of this, the reason the argument for doing this problem is that we're thinking about outflows, river outflows into the ocean. In particular, the fluid tends to be less dense than the environment, so it's either warm or it's fresher, and so it floats on the surface. And because it's on the rotating Earth, it sticks to the coast. In general, in the northern hemisphere, it'll stick to the coast with the coast on its right, so it can move out the coast on its left as well. And the aim is to derive an equation for the boundary of this coast. So as you can see, it's much narrower than it is long. So we'll try and derive a long wave equation that describes the displacement of the edge of the coast, of the edge of the current from the coast. Here's another example. They pulled a dam out up here and this muddy water came down. And again, you could see it's moved out and turned to the right. In the Olympic Peninsula, down there, Seattle. People do experiments on this, do it in a rotating tank. They're looking down on a rotating tank. They pump out light dyed fluid into a sponge actually here, and then some of it travels around, some of it sticks around. It tends not to be observed in flows in the oceans, this idea of this giant blob sticking around. And part of the argument is that it's because this is negative relative vorticity. They pump it out and the tank is positive rotation, it's anti-clockwise. This fluid, the way they force the flow tends to be clockwise rotation. And I argue that that makes a difference. What's the dynamics we're going to have here? Well, the dynamics gets us to the Kelvin wave. What is a Kelvin wave? It's nothing more than a free surface water wave. Because you're in a rotating domain, it piles up on the right hand, on the right, it piles up at the coast to its right. But it's just really a free surface water wave. There are other waves at the edge of the current. Then there's a Rossby wave, and the Rossby wave is a so the Kelvin wave is a vertical fluctuation. The Rossby wave is a horizontal fluctuation in the edge of the current. It's because the current has vorticity, and it is a unidirectional wave, and it propagates with high vorticity to its right. The Kelvin wave, I should have said, propagates with the wall to its right. So these two waves can either superpose or they can oppose each other depending on the sign of the vorticity. And then there's image vorticity in the wall. What governing equations shall we use? We just use shallow water equations. Here are the rotating shallow water equations. There are two classical limits of these equations, the so-called semi-geostrophic equations and the quasi-geostrophic. So today I'll talk about the quasi-geostrophic equations, and we're making the assumption that the vorticity that's in the exposed flow, the vorticity in the flow that we expel, is going to be small compared to the rotation rate of the Earth. And that will eliminate all those colored terms. It makes the momentum equations linear, but in fact it makes the depth a stream function, as you can see there for the flow. Where's the dynamics? The dynamics is that this quantity, known as in the jargon as the potential vorticity, is constant. We get that just by cross differentiation. And it really plays the role of the vorticity in the 2D Euler equations. if H was a constant and F was 0, it would just be the vertical component of vorticity. So this system is going to look very much like the 2D Euler equations. What are our two physical setups? Well, this is probably the most likely one in the ocean, that we have a shallow river coming out, and we have a deeper layer of ambient fluid of the same density sitting outside in the ocean, floating on a, in this case, infinite layer of much denser fluid. So the fluid comes out here, stretches to join the same length as the ambient fluid. So because it stretches, if you like, it generates, it amplifies its vorticity, generates positive vorticity, positive relative vorticity. And so an ocean current tends to have positive relative vorticity. The experiments have, well, they measure it, it has got negative relative vorticity that can occur in the ocean. The only way it's going to occur is if you have an outflow with a sill, and that can hold back this dense fluid. And so when the lighter fluid comes out, it's compressed. Because it's compressed, it generates negative relative vorticity. And today, most of the time, I'll concentrate on this case because it's more interesting, as we'll see. It's when the Rossby waves oppose the Kelvin waves. So the whole problem here is determined by the boundary of the current after it's come out. Because if something's inside that boundary, it's expelled fluid, so its vorticity is 1 or -1, which is scaled in. And if it's outside, it's 0. So long as we know where that boundary is, then we know the entire vorticity distribution for our flow. Because of that, we know the boundary conditions, we can invert and find the flow. So this is a very classical problem in 2D Euler mobility. We'll then eventually, I'll call that boundary C, but we'll eventually assume the long wave approximation that it's single value, and then the boundary will be given by capital Y, X and T. And it's capital Y, which is going to be our variable that we want an equation for it. So what are the governing equations? Well, I think we've already said that the momentum equations just say that the interface displacement, our eta, is going to give us a stream function. That potential vorticity in this limit just becomes the modified Helmholtz operator. So it would be just the Laplacian as in Euler, but in fact we get an extra term because of the deviation of the surface. So it's really just the modified Helmholtz operator. And there's only one parameter in the problem, and that parameter is A, 1 over A. And A is a measure of the density variation. The stronger the density contrast between the two layers of fluid, the bigger A is. What are the boundary conditions? That's the only other thing we need now. The boundary conditions, well, we just say what the normal flow is at the wall. So we're going to have a wall where there's no normal flow, except we'll have a gap, and out of that gap will come fluid, and we'll specify the outward flow velocity. So that's V there. But V, we already know, is from stream functions. We can integrate that up, and that gives us eta on the wall. So we now have eta on the wall, and we have del squared eta in the interior, if you like. So we can just invert and find eta everywhere, and therefore we find the velocity field everywhere. And this is a classic technique. It's being made into a very powerful numerical technique, contour dynamics, and it's used a lot in 2D Euler. But it works just as well for this problem. It works better because the Green's function decays exponentially. How do we turn this into a long wave equation? Well, we turn to a long wave equation. First of all, the interface condition is the same as on water waves. A particle on the surface remains on the surface. A particle on the interface between the current and the open ocean stays on the interface. So that's the interfacial condition. And then we just say that the X scale is much longer than the Y scale, due to the X. We just cross that out of the equation, it's a leading order. And we get an equation which just is an overlay in Y. Boundary moves with X and T, so X and T appear parametrically. So we can just solve this equation, substitute it in here, and we've got a long wave equation. And that's the equation at the top. It's which is first order, so it's a hydraulic equation. It's a first order PDE. This is our flux function here, and then we can integrate that. And as I said, I'll just concentrate on negative PV where it does worst. There's an example where I guess with an outflow with 20, comparing it with the integrations of the QG equations, the hydrodynamics. And you can see it captures the general behavior. What it doesn't capture, of course, is Rossby waves propagating away from, this is the source region here, I should say. This is the unforced region to the upstream, if you like. This is the unforced region downstream. We have a rarefaction here, which is captured well. It captures well the development of the flow to actually, it develops a critical point here. This is a controlled flow, and then it captures this upstream flow, but it doesn't capture the Rossby waves. This is the same geometry, but at a slightly larger value of this parameter A. That corresponds to slightly stronger vortical effects. Let's now go to a much narrower shelf. You'd expect that the hydraulic theory would fail for a narrow outflow. W, I'm sorry, is the width of the outflow. This is actually a delta function outflow here. The red line is the hydraulic solution. The blue line is the QG solution, the full solution. And now there's quite significant differences. You can notice that upstream gets the width slightly wrong, and the upstream has two layers. It has a layer here, then a rarefaction, then a different constant width. And downstream again, it isn't a rarefaction right from the control point. It actually has a flat region, a shelf, and then a rarefaction. So can we capture those? Well, first of all, can we explain maybe the upstream condition? I think you probably guess what's going on in that here's our hydraulic solution and the flux function. Of course, there are values of A for which the flux function is non-convex. So here's our flux function for this particular value of A we've chosen here, and it's non-convex. So that means that it doesn't satisfy the lax condition because the gradient of the shock does not lie between the gradients of either end. The gradient of the shock is larger than the gradients of either end. And you know the resolution to that. The resolution is the largest shock you can have is the one that's tangential to the curve, and then there's a rarefaction that joins them. And that's what we've done here. This is just a Riemann problem using those equations, and this was the initial state, and this is what it's evolved to translated to the larger state, and that's the highest possible drop you have. So that partially explains what's going on, but does not give us any constraints on the widths of the current. So how can we get the widths of the current? And the way to do that is, of course, to go to the next order. Here's the top line here is our hydraulic solution. We've gone to one order further in our expansion. And of course, that brings in dispersion. So that's our governing equation, our dispersive equation. What do we want to do with this? Well, the usual stuff. We can look away from the source region. Q is a constant, and then we can do the normal potential theory. Here is the potential form of the equation. We'll have traveling wave solutions. these are the typical things that you'd expect to see. That this one here, of course, is we have two simple zeros, so it's a periodic wave train. Here we have a zero and a double zero, a solitary wave, two double zeros, a kink soliton, and a new one really, a double zero where the solution can get down to the wall. I would call this an intrusion. It's just something that comes out of the wall, goes up and has constant width, so constant width current. We can now build up a solution to the steady problem by, first of all, we can demand I should say the black line here, the solid black line is the QG solution. So this is the full steady solution to the problem. And the dashed line is the dispersive solution. This is for the width of 3. This is for a width of 10. We'd expect the wider one to be closer, of course. How have we built up this solution? Well, no rocky waves can stand against all the rocky waves propagate downstream, so none can stand on the downstream side. So downstream, the flow has to be flat. Upstream, we must have one of those solution of the dispersive equation. We have to have a solution of this equation. So in fact, it's a solitary wave upstream. So it matches onto a part of a solitary wave here, standing on this value. And then here, the solution is forced. And we haven't found any simple way of solving the forced equation. We just solve the forced equation numerically by insisting that it matches the solution to that dispersive equation here and that it's flat here. And that gives us a unique solution. And that's the comparison with the hydrodynamics. One place where we can do something with the dispersive equation is where it doesn't apply. We can do something where we let W go to 0. Let the width of the region go to 0, then the black line again is the hydrodynamics. This is the long wave equation for W equals 100, W equals 10, W equals 3. And remarkably, it seems that the long wave equation is capturing the behavior when W equals 0, when Y. And this works even better, well, just as well. This is the height from the hydrodynamics. This is the prediction from W equals 3. And it seems that the long wave equation is doing very well, even at W equals 0. One thing you can see is the structure is unusual. If you look at the long wave equation, it's developing a vertical region here, and then it's got the solitary wave. And the solitary wave is flat. This is really, it's trying to form the largest possible solitary wave that can exist upon this level. And then when it can't get any higher, it joins with the shock. So if we postulate a structure which consists of the highest possible solitary wave on some level Y plus, it goes up to some level YS, and then has a shock up to this Y minus value. We can then integrate, we can then find a jump condition by integrating our dispersive equation across this region. This is our jump condition. We have a condition that the flux must be conserved, and we have a condition for the solitary wave. That gives us sufficient conditions to determine all of our 3 unknowns. We can determine Y plus, YS, and Y minus. And really, that's how these predictions work. These predictions here are determined. So it seems that those 3 do give us an estimate of what's going on at W equals 0. So in some sense, we now know what's happening at the origin, around near the source. So that's determining the width of the upstream and downstream currents. So can we have a look at what happens at the other end of those currents? So that depends very strongly on the values of vorticity. So here's one where A is 1.3. This is quite a small amount of vorticity in the flow. And what we get is we get an intrusion. This is a unique intrusion given the value of A. That determines the height of the intrusion. And then this is the value here that we've determined at the origin, and then linked in this case by a rarefaction. Of course, the ends of the rarefaction are just the long wave speeds for that height and for that height. And of course, you just check that the slope of the intrusion is what you'd expect from that dispersive equation. If we increase the vorticity in the flow just a little bit actually to 1.75, then this is the unique, you can see the unique intrusion there that determines that height. Now that height actually is higher than the value of the flow coming out from the origin, and so they're linked by a dispersive shock wave. So this shock wave, I think because these waves are not quite get caught by the Gennadi's theory, the prediction for the theory from the theory is good, but it's not perfect. It predicts the front of the DSWs here, and it predicts the amplitude of the DSWs there. The only change between the top picture and the bottom picture is we've made the source wider. So we should have decreased the dispersion. What it does is those long Rossby waves we saw very early on in the hydraulic pictures coming out, and they're propagating through the dispersive shock wave. They're propagating out right out to the front, where they're becoming, well, solitary waves, solitary waves here at the front. And so the structure, DSW structure is breaking down. Well, this is we've seen it already. This is Gennadi's theory for predicting the speeds and amplitudes of the front and back of the DSW. And then finally, if we increase the vorticity even higher to 3, then we get a train of these half intrusions, the periodic train of intrusions, and we get a DSW at the back. The leading order soliton for the DSW is faster than this train propagates, so we only get a partial DSW. These partial DSWs that have been found before, of course, they've been analysed in an NLS problem by Mark Hofer, but the advantage of doing it there is, of course, that you know the underlying wave. You've got an analytic expression for the underlying wave. We have no analytic expression for the underlying waves here, so we can't predict where the junction is. Unless someone can make a suggestion, we can't predict where the junction is between the DSW and the periodic wave train, because we don't have the initial conditions for Gennadi's ODEs. And so just a summary, we looked at the unsteady force dispersive equations for outflows. In the near field, you could solve for general W by demanding that it joins a solitary wave upstream and is flat downstream, but you've got to solve that numerically. We have to solve it numerically. If you take the limit W goes to 0, you can then reduce that to a set of algebraic equations, which seem to match the full solution. They give the right prediction for the current widths, which is a little strange, and it seems to say that somehow you're capturing some conservation relation in the problem. And then for the far field, it starts off as an intrusion rarefaction. Increase the vorticity, it becomes an intrusion DSW. You increase it a bit more, it becomes a wave train with a truncated DSW. Some small, those are mainly the basis for the current work.
We have a question, Prof. Yes?
I was wondering if it's a spectacular picture to show the physical right on the Olympic Peninsula. Is there any evidence in that picture that we should be looking for to start to show that picture?
In fact, yes, I haven't got the slide here. You could actually almost, that one, rightly, it seems like A must be very large there because you can do if you assume that A is infinite, so you've got the Laplace equation, you can almost get that shape analytically if you were uniform vorticity in the Laplace equation coming out from the whole of the wall. So the chances are that that one there is A equals infinity.
Any other question for Kelly? I have one actually. More at the end of the talk. So when you apply the analysis method to obtain the solid edge, what is the dispersion relation that you because in the ODE, maybe I missed in the talk.
What do we need? We need, yes, so
Okay, so
yeah.
because everything it's so in K it's only a polynomial in K, right? But omega only depend. It's a polynomial in K, right?
yes, yeah,
Okay.
yeah, we've expanded in K there, yeah.
Okay. It's an expansion in K.
So, yeah, that's, yeah, just from the. Is it? No, I think that's the full thing, yeah, but.
Okay, so it's no
Yeah.
expansion. Okay.
And I should say that this is the only, one of the only cases where this, Gennadi's theory doesn't work. Everywhere else, I mean, it doesn't work perfectly. Everywhere else, it, works beautifully. I'm showing you lots that don't work.
Any other question? Okay, if not, let them say it again.